this is the second half of the thermochemistry basics lecture slash background information, where I'm going to talk specifically about calorimetry, because the basics of calorimetry, I feel fairly confident that you already understand. Even if you perhaps didn't define the term in Regents, you certainly use the idea. Calorimetry, by definition, is a tool for studying heat exchange. That's what calorimetry is, coming from the term calorie, which is a unit for energy. It's based on the concept of conservation of energy. It's based on the concept of heat lost has to be equal to heat gained. That if one object loses a certain amount of energy, something else must have gained it. That's the whole idea behind calorimetry. And typically, what calorimetry is used for is figuring out heat capacities of different substances, and also figuring out enthalpies of reaction. And it's used most practically in figuring out calories in food. That's how the amount of calories in food are figured out is through the use of a calorimeter and through calorimetry. They literally they do something so that they can transfer all of the energy that's in the food to something else, and then they sort of measure the something else and work backwards and say, well, this is how much energy must have been in the food. The way nearly all basic calorimeters work is they have to have some element of design that ensures, and this is a big important point, that virtually all of the heat is transferred from one substance inside to another substance inside. So you've got two things inside. We've got an insulated lid, an insulated ring, so there's lots and lots and lots of insulation. That's an important thing about a calorimeter because, as I said, the point is to look at heat transfer. So calorimeters need to be designed so that as much heat as possible is transferred directly and isn't lost to the ambient air, the ambient environment, that it is as much as possible direct transfer. Now, I say it's a transfer between two substances. Water is very commonly used as one of those two substances. It's usually water and something else. Water and the food that you're interested in figuring out how many calories it has. Water and a metal that you're trying to figure out its specific heat for. Because we know a lot about water and it's very easy to get our hands in water. We also have a thermometer, as you see, and the thermometer is measuring the temperature of the water. Typically, almost all calorimetry experiments work. A hot item, well, it doesn't have to be hot, but an item is placed into the water, and the temperature of the water will change because, as we talked about in class, if you put something that's hot, combine it with something that's cold, you will get a transfer of thermal energy from the hot item to the cool item until they both have equilibrated their thermal energy and they are both at the same temperature. So what we measure in calorimetry is the change in temperature of the water. And we know the water's specific heat really, really well, so we can use that to figure out, well, if the water went up by a certain number of degrees or went down by a certain number of degrees, how much energy is required to do that. And then we know that that energy must have come from the other object that was in the water. That's the idea behind calorimetry. Heat capacity, it's all based on heat lost is equal to heat gained. That's really the fundamental crux of calorimetry. But there's also a note that is worth mentioning, that when we're talking about heat capacity, water will certainly be the major contributor to energy absorption in a calorimeter. But the calorimeter itself, the physical components, the styrofoam cups, the beaker that you placed it in, that will have a certain capacity to absorb heat as well. So when we talk about a calorimeter as the whole, it's the two things that you've really got in it. You've got the water that's in it, and then you have C empty. This would be your cups, beaker, etc. This is styrofoam. So the heat capacity of the calorimeter as a whole is going to be adding those two things together. How much water do you have? What's the heat capacity of the water? How much can the cups absorb on their own? You add those two things together, that's going to be the total heat capacity of your calorimeter. Now you can then take this idea and really apply it, and this is really what we're going to be using in calorimetry. to say that the heat lost by the substance is going to be equal to the heat gained by the water. And you'll notice we've got Q water equals negative Q substance. We have a switch in sign here. The substance is losing heat. That's exothermic. We mentioned that that's a negative sign, so you see we've got a negative sign here. Heat gained by water, that's endothermic. That's positive. We have a positive sign here. Heat lost is equal to heat gained. It's the same amount, but it's just in a different direction. But because this is both Q, heat of the water, heat of the substance, and we know that Q is equal to mc delta T, mass times specific heat capacity times change in temperature, we can therefore make this statement, that mc delta T is equal to negative mc delta T. The mass of the water times the heat capacity of the water times the change in temperature of the water is equal to negative, that's a really important thing that you need to notice is there, the mass of the substance times the specific heat of the substance times the change in temperature of the substance. We're going to be using this idea in problems in class. We'll be discussing this specifically, so if you have questions, please do not hesitate to ask.